Alrighty, guys. So I'm going to go over a couple of basic things that we need to have before going into calculus stuff. And one of those things is evaluating a function. So I'm going to show you real quick how to do this, but I'm not going to actually do it for you. So if I have this function f of x equals 2x squared minus 3x, we know it's a parabola. We know it's facing up because it's a positive number for the x squared. What is f of 5? So I'm not going to show you how to do this. So all you gotta do here is take this 5 and plug it in for every x here. So you'll have 2 times parentheses 5 squared minus 3 times parentheses 5, then calculate your final value. It's literally as simple as it is for when you're plugging in a number. So now I'm gonna show you something with something a little bit different. Now I'm gonna show you with x plus h. So we're gonna be dealing with x plus h a lot, so get used to it in calculus. What I'm gonna do now is I'm gonna take x plus h, and everywhere I see an x, I'm replacing it with x plus h. So this should look like 2 parentheses x plus h. That's what I'm subbing in here. Oops, not 1, x plus h, quantity squared, minus 3, and everywhere you're plugging it in, you want to put parentheses x plus h. Remember, I'm subbing it in there. So now PEMDAS tells me when I'm simplifying, I'm going to take care of my exponent first, then I'm going to multiply, then I'm going to add or subtract. So 2 times x plus h squared. The shortcut to that is to say x times x is x squared, and then x times h is xh plus another xh gives me 2xh. I'm going a little fast there, but make sure you boil this out, and you're going to get what I'm, basically, you're going to get what I'm saying, okay? So I'm skipping because we're now in calculus. So then you get 2xh plus h times h is h squared. And then minus 3, I'm distributing here. I don't have to take care of any exponents here. 3x minus 3h. I'm distributing in negative h. Negative 3, I'm sorry. So then lastly, I would distribute and then add any like terms. So 2x squared plus 4xh plus 2h squared minus 3x minus 3h. And then lastly, combine like terms. I don't have any like terms. So all I would do is bring this h squared to the front because that's my highest exponent. I would like my highest exponent. So 2x squared plus 2h squared plus 4xh minus 3x minus 3h. That would be that final thing simplified. And then finally, we're going to see this a whole lot once after our limits unit, but we're going to have to plug in both x plus h and x into my function. So we already know what it looks like with f of x, and we just plugged in f of x plus h from here. So part C should look like this. So from plugging in x plus h from B, this is what we got. And then I would still need to subtract f of x, which is given to us here. So minus 2x squared minus 3x. And remember, I'm subtracting that entire thing, so it's super important for you to put parentheses. So remember, this is f of x, and all of this is f of x plus h. So now I'll go ahead and remove that underlining because it makes it look a little weird. Now I would actually go ahead and handle this all together. So if you want, I can rewrite this as 2x squared plus, I'll rewrite it all. Fast forward. Okay, so now I fit all of this in one line where I distributed the negative here and here, so that gave me a minus 2x squared and a plus 3x. So now all I would do is cancel out or combine my like terms, and we're going to see a lot of stuff cancel when it comes to this component. So I have 2x squared here, 2x squared here, positive, negative, cancel each other out. Then I have a minus 3x here, a plus 3x here, positive, negative, cancel each other out. What am I left with? 2h squared plus 4xh minus 3h. That would be my simplified version. So yeah, this will be some tedious stuff, but you should be able to catch on to it pretty quickly. You're just plugging stuff in and then evaluating later. All right, so another really important part of calculus is being able to find the domain. We've already found evaluating functions. We're good there. Find the domain. To find the domain, you need to think of what things you cannot do. So let's look at x squared plus 5x plus 1. First of all, let's think about what that makes, what shape of the graph that makes if we can. That's super easy because it is a parabola facing up. So the domain of any parabola or any quadratic function, the domain would be all real numbers or negative infinity to positive. Nothing crazy there. So let's move on to our second function. So 3x over x plus 3, this is a rational function. This is where you get your asymptotes, your vertical and horizontal asymptotes. So when it comes to these, remember your vertical asymptotes, the part that is not defined from rational functions are two places. discontinuity, removable discontinuities, and vertical asymptotes. So removable discontinuities, remember, come from canceling things out. Here, if there's an x plus 3 on top, then we can cancel it out, but there is no x plus 3, there's just a 3 times x. So there are no removable discontinuities, aka no holes. But instead, we look at the bottom. Remember, what can you not do with a number? You cannot divide by 0. You can multiply by 0, you can have 0 up top, but you can't have 0 on the bottom. So we want to figure out, for our domain, we want to figure out what number makes this equal to 0. So what number makes this equal to 0? If I solve algebraically, set it equal to 0 first and then solve algebraically, I get -3. So my domain is going to be all numbers from -infinity to -3, union -3 to +infinity. Okay? Okay, so the last one that I wanted to go through was C, which we have a square root of x minus 9. So remember, when it comes to square roots, you want to think, what can you not take the square root of, or what has to be under your square root? And the only numbers that can be under your square root are positive ones or 0. So there cannot be any negative numbers, or else you get an imaginary value or a complex. So what you'd want to do here is make sure that x minus 9, whatever is inside of your square root, is greater than or equal to 0. So you'd have to set up an inequality there, and then you would go ahead and solve for that inequality by adding 9. So x would have to be greater than or equal to 9. You would think to yourself, any number that I plug in that's bigger than or equal to 9 will keep this positive. If it's less than 9, like 8 minus 9 would give me -1. 7 minus 9 would give me -2. And then all of a sudden I have a square root of a negative value, which would give me an imaginary number or a complex number. So my domain here would be all numbers greater than or equal to 9. So remember, equal to is the bracket from 9 to infinity. That pretty much covers domain of a function. Now I want to talk about the parent functions very quickly. All right, so let's talk about the basic parent functions that you need to know. The reason you want to know what the parent functions look like is to be able to graph better, but also to be able to find the domain better. So I'll go ahead and quickly talk about these. Remember, our basic one is a linear function. Y equals x would be that function. And the whole point of doing that is to be able to determine that the domain, since it goes from left to right, is -infinity to +infinity, and same with the range, goes from bottom to top. Okay? So a quadratic function kind of has the same domain from -infinity to +infinity, but the range is limited. So you'd have to figure out what that bottommost point is on a parabola to figure out what the range is. Real quick, a cubic one kind of looks like this. That's a degree 3 polynomial where the domain is -infinity to +infinity, and the range is -infinity to +infinity. It goes from bottom to top. Next, we have the square root of x. I'll go ahead and put that there. That is the equation y equals square root of x would be the function there, graphed. And this has a domain of, now it's not from -infinity to +infinity. It starts at 0 because we can't take the square root of anything that is negative. So I'm going to include 0 here, 0 to infinity. And then the range would be also from 0 to infinity, because you get positive numbers out of that. When you take the square root of positive, you get a positive. Another parent function that you want to keep your eye on is this guy right here, y equals 1 over x, the parent rational function. We'll be dealing with this a lot. This is where you get your vertical and horizontal asymptotes. So when you see something like that, you probably have a fraction polynomial. So if we look at this, the domain would be from left to right. It goes from -infinity and it stops at 0. And then it continues from 0 to infinity. I had to squeeze that in both lines. The domain for that one would be there. And then the range is the same thing because it goes from bottom to top, but it stops at 0 as well. So I won't write that down, but just know that is a unique one where it doesn't have 0 in its domain. That's the only number that it doesn't have. All right, and then finally, I'm going to go over the last two that we need to be aware of going into this. So one of them is the parent exponential function, which looks like this. So we're going to call this y equals e to the power of x. Okay, so this one doesn't have a vertical asymptote like the rational functions, but it does have a horizontal asymptote. So your domain, because it has no vertical asymptotes, no stopping points left to right, is -infinity to positive infinity. However, your range, because if I take e and raise it to any power, whether it's positive or negative, I'm never going to get a negative value, nor am I ever going to get 0. Okay, so my range here is going to be from 0 to positive infinity. It starts at 0, and remember, it gets closer and closer to 0 from the top, but it never actually hits it. So 0 to infinity would be my range. Okay, and just very quickly here, I wanted to go back to my exponential function and put down the point 0, 1, because e to the power of 0 is 1. Any number to the power of 0 is 1. That's the key point for that one. And I want to invert it here for my natural log function. So remember, exponentials and logs, they're inverses of each other. So if the coordinate point is 0, 1 over here it has to flip, which means this coordinate point would be 1, 0. Okay? So remember, since they're inverses, they're reflecting across this line y equals x. So if I were to have them on the same graph, there would be a reflection across that. Which means, since there's a horizontal asymptote over here I have a vertical asymptote. Okay? So that changes things a little bit. Now, my domain is going to be from this number to the positive infinity. Well, what is this number? This number is 0, and there's a vertical asymptote there. So we're not going to include 0, and it's going to go to just positive values for x. So 0 to infinity would be my domain. And then my range, as you can see, it goes down here and up there. So it goes from negative infinity to positive infinity. My range has no limit there. Okay? So it's important to know about those 1, 2, 3, 4, 5, 6, 7 functions going into calculus.